So today, what I'm going to be talking about is some techniques that Heimdall has used in order to. We have a product that actually allows you to automatically scale out the SQL databases. But I'm not just going to talk about how the product works. I'm going to talk about the techniques that are used by the Heimdall proxy, and then at the very tail end, I'll talk about the proxy itself. So this actually is somewhat targeted for developers and talking about techniques that can be used on your own. So what we're going to be talking about is first, if you're going to be creating cache, some of the issues that you're going to come up with when you're rolling your own solution for caching, and how a data grid type product can be used in order to implement this. Then at the tail end, we'll talk about how the Heimdall database proxy and other proxies work and how they can solve problems on your behalf so that you don't actually have to do the work. My target is to talk about how the issues are resolved to a level that you don't want to do it yourself, but hopefully you'll get some good ideas on what you can do and techniques you can use if you wish to anyway. And then at the tail end, go into Q&A and possible demo time permitting. Okay, so first off, as far as the scaling of databases, there are two main features that we will talk about, and they're actually more related than you think, or most people would think. The first one is caching, and that is leveraging a data grid or similar as a high-speed storage layer that stores the results that are coming from the database, and then reusing them as needed. The second feature is ReadWrite Split. So in many environments, you have the ability to have multiple database servers. You have a write-only server, and then you can have read-only servers as well. And we'll talk about the techniques that are needed in order to effectively leverage the read server without causing data corruption. And both of these together provide the scale-up functionality that we will be talking about. Now, first off, let's talk about rolling your own cache, okay? At first, you would think that a cache is very simple. All you need to do is take the data that was retrieved from the database, create an appropriate key based on the query, push it into your data store, key value store, and then when you have another query, you simply pull the data back out of that key value store based on the key. Okay, however, the big question is, first off, and one of the hardest topics in computer science is invalidation. How do you invalidate data within the data store? Additionally, another aspect that most people don't think about is that cache misses when, say, you're pulling from a data grid, they take time. If your cache hit rate is not high enough, then you can actually slow things down by adding a layer to the cache engine, or adding a layer to the processing just to ask if you've got an object. Okay. Additionally, are you over caching? You could be putting in objects that you're never going to query again. Maybe because they have a timestamp associated with the query. After 1 second, you'll never make the same query again. Finally, have you accounted for the security of the objects? If all you're doing is using the query as your cache key, people could potentially bypass controls on the database to say only one user or set of users should have access to the data. Now that's in the cache, anybody could pull it. And then finally, debugging can be very difficult depending on how the cache engine is set up. So these are all topics that if you're building your own cache, you're going to have to deal with. But let's actually talk about some of these and how they can be implemented if you're going to do so. Invalidation. The hardest part of caching, obviously, is knowing what to throw out. So when dealing with a SQL database, the easiest way to understand how to throw out objects isn't necessarily to look at a row or result set basis, but you want to categorize the queries and results. And the easiest way to do it is by table. So if you make a write to a table, you want to invalidate the objects that were stored from that table. Now, with Heimdall, the way that we handle this in order to make this very efficient is that we use a timestamp on each table to know when a table was written to. We can then simply look at the table and that timestamp when we retrieve a query from the result and say, was this query or the result generated before or after the last write? If it was before the last write, we throw it out as being stale, and we pull in a new version of the object. This is very efficient because one of the things that you don't want to do is you don't want to walk the cache. If you have tens of thousands of objects and you do a write, you don't want to have to actually check each of those 10,000 objects to see whether or not it may now be stale. Okay, you just wait until you actually try to use it. When you figure out, it's stale, throw it out. Okay, and then what you want to do is leverage functionality that's provided in in-memory databases to expire the objects after some finite period of time so that your cache doesn't grow to infinity. So the idea here is that you can set up your cache rules to cache into the engine, but the engine is set to only cache an object for 10 minutes or an hour or a day, whatever makes sense for your application. Now, if you're dealing with a distributed application, this becomes much harder. Okay, and most cache engines, like in Hibernate and such, they don't do very well in optimally handling everything because they're really not designed to do invalidation at a global level. What they're actually expecting is that when you invalidate an object, you delete out of the cache, which may be in your grid cache. But in order to do that, you have to keep track of every object and walk those objects. That doesn't scale very well. Instead, what you want to do is leverage the pub/sub interface that's provided on most in-memory databases like GridGain, Redis, Hazelcast, whatever. You send notifications to each of the other nodes that you just wrote to a table. They now know, these other nodes now know that the table has been written to. They update their last write time, and if they pull an object that's stale, they're able to invalidate it and refresh it, and everybody's good. Okay. One last aspect of this particular piece is that those invalidations, you do not want to send every time there's an actual write happening, because you can then flood the pub/sub interface and you end up with as many messages as you do writes against the tables, and that can slow things down. Instead, what Heimdall does is it creates a sliding window of effectively flagging tables as being active. And in the case of Heimdall, if we see a write against a particular table, we'll send a message through the pub/sub interface saying, this table is being written to at this time, and for the next 2 seconds, consider it to be non-cacheable or being volatile. If after 1 second it sees more activity, it refreshes that window. So for every table, any proxy node will send out no more than 1 message per second. And that allows it to scale very effectively, even if you're doing hundreds of thousands of inserts or updates against the database, even if you've got many, many different tables involved as well. Okay, if you have any questions, you can post those. I'm keeping a tab on the chat window if you have anything. Okay.
Yep.
Now, the next thing is to try to reduce the latency impact of doing the caching. If you're using a in-memory database and you're caching into a separate node, let's say centralized in-memory database, you're still doing a network hop in order to get to that database in order to ask it a question. And that network latency can be a substantial amount of the time it would take just to ask the database the question as well. So the whole point is you want to reduce latency in sum total, and you need to reduce the number of round trips all over the place, not just the database. So one of the main techniques that we use in Heimdall in order to reduce the impact of latency is we leverage another feature of in-memory databases, and that is key tracking. So all of the popular in-memory databases support the ability to send a notification message to listeners whenever there's a particular data or there's a change to what keys are available. So Heimdall listens to that notification list, and it stores a list of all the keys locally, so we can look up whether or not a key exists in a remote data store before we ask that data store for the result associated with that key. Net result of that is that we can avoid the round trip penalty on a cache miss. We only go to the cache or the in-memory database when we know that there's something there that we may want to use. Okay, and that improves things dramatically. Okay, now another aspect about reducing latency, and this is a particular aspect dealing with how the proxy works, is that if you have to ask the in-memory database on one connection and you open the connection, pull the data, close it, then you have to go to the database itself. Well, with the way that the architecture works with Heimdall is you simply send one request to Heimdall, the proxy that's doing the caching and doing all this logic for you, and it will give you an answer. You only have to have one round trip in order to get that. And you don't have to implement the logic on your application to do that. One of the problems that many environments have, and I'm going to call out PHP because this is a big offender, is that you open a connection to the in-memory database on every page view. You try to get the data, you may have a cache miss, you then close the connection, then you open a connection to the database in order to pull the data. Then if you pull that data in, you can then push the data back into the in-memory database. But you're adding lots of extra steps. By going in particular in that type of a threading model where you can't have state carried over for connections from one thread to the other. What you want to do is ensure that you ask one source for the data and it does whatever needs to be done in order to optimally pull it. Okay. Now, in a PHP environment, because it's not sharing state, you can't use many of these tricks that I'm mentioning. But if you're, say, using Java or something else, a Java type of environment, where everything is purely multi-threaded, you can do this. And you can keep track of the keys that are in the remote cache. You can use rules to, for example, figure out what tables it makes sense to actually do caching for. You may find that you never get a cache hit when a query involves a particular table. If that's the case, you can stop caching for that table and never take the overhead of dealing with it. Use local memory for frequently used objects. Again, if you're using an environment like Java that uses some has the idea of what's called soft references, or the garbage collection can delete objects if they need space. Soft references are great for storing objects that are being cached, because you just put it to the side. If you need it, it's there, but if the system needs more memory, it can free up those objects and they just won't be there and you pull from the database instead. One final piece of latency that a lot of people don't really think about is serialization. And that is taking a data structure, converting it into a stream of bytes, and then in the reverse side, when you're pulling from the cache, taking it and reversing it back into a data structure. Serialization is definitely something when dealing with caching you want to benchmark, and there are various libraries that work better or worse depending on the type of data that you're dealing with. Pay attention to it, optimize it, and use the best serialization technique before putting something into the cache. Okay. Now, more can be less. Don't cache everything. Let's assume that you have a cache that's set up to store 4 gigabytes worth of data in memory. You then have a database that is storing large blobs, and you have a result set that can actually be 4 gigabytes in size. You should never put that result set into your cache. It's not going to give you enough of a benefit. Okay, once you get into a streaming result with a database, they can stream that data generally very, very quickly. And it's not going to give you much of a benefit to try to push it into an in-memory database. And by the way, by pushing 4 gigs of data into a 4 gig data store, you pushed everything else out of that cache. You don't want to do that. Okay, so pay attention to the size of the objects that are being stored, set thresholds that make sense, and then allow the cache to use, say, an LRU type mechanism in order to optimize the use of the cache. Again, categorize the data, figure out what tables aren't providing a benefit and stop caching for them, maybe periodically revert the behavior, kind of age out that information, try again later. At different times of the day, you may get different results from different tables. Okay, and then finally, track invalidation frequency. Adding to this list is one more point that we have implemented, and that is even in memory, using a 2-tier ingestion strategy. The idea is that you don't want to flood your long-term cache with objects that you're never going to use. You want to push in objects that are actually useful. So what Heimdall has implemented is an ingestion gatekeeper that is a limited number of cache entries. And that itself is an LRU system. If an object is not retrieved out of that initial tier, then it will never go to the second tier of long-term cache, which is where most of the space is allocated to. So your initial ingestion may be, say, 1,000 to 5,000 entries, and your long-term store maybe 100,000 entries. If you don't get a cache hit before it expires out of the 1,000 entry list, you never put it into the 100,000 entry list. And this allows you to keep from throwing out objects out of your long-term store that may be used, whereas the new object never will be. Okay, caching can be very complex in order to get everything just right and adaptive and work without having to fiddle with it. And that's the type of thing that Heimdall has tried to do, is to take that burden off your hands. Okay, next part is the security. So when you create your cache key, you can't just use the query itself. You've got to put in every piece of information that could be used to authenticate a user for access privileges. And then an interesting point is that you also want to include, as part of the cache key, any variables that impact the output presentation of the result set. So as an example, you may have a database that has that negotiates character set for different users that are coming in from different regions of the world. You want to include the character set that has been negotiated with the client as part of your cache key. That way, if someone else comes in and has a different character set defined, you don't give them the wrong result. Additionally, the username. In most databases support the idea of database instances within a database as well, often for multi-tenancy. So on your database cluster, you may have database A, database B, and database C. Each one of those may have an identical schema and identical table names. You can't cache just based on the query because the query may not contain the name of the database instance. So you want to ensure that when you create your cache key, the database instance name is included as part of that. Okay. Finally, when dealing with everything, I'll talk about serialization again. There could be serialization vulnerabilities. This has been something that has cropped up with Java and many other environments often, where if you give any sort of control over the data that to a user that has been serialized, they could modify the serialized data in order to inject and change behaviors within the system. So if you're caching things in a way that could be exposed to users, be very, very careful about the security vulnerabilities that could come into play. Also, pay attention to what encryption is necessary. If you are caching and storing on a local instance, you could consider that to be data in flight, and you may not have to encrypt it. But if you pass it over the wire to a shared in-memory database, you may need to at least use TLS to encrypt it over the wire, or you may need to encrypt the data before it even goes into the in-memory database and then decrypt it when it comes back out. Okay, leverage the capabilities that are included as part of your in-memory database libraries. Definitely analyze what the security requirements are, whether you're dealing with, say, PCI or HIPAA data, or even just PII. Okay, and make sure that it's secure. Okay. So at this point, we're going to be moving on to ReadWrite Split. Now, I'm going to step back on this. This is actually a very easy concept to master or to think about, but most developers don't really think about the nuances of this because they don't understand how the database works when you pull data from a reader in a database cluster. And one of the most important parts is replication lag, which I'll get into in a minute. But the deceptively simple part is you just open up two connections, one to the writer, one to the reader, and send reads to the reader when necessary, right? Okay, seems simple enough. But the replication lag between databases becomes a big issue. And I'm going to use SQL Server as an example here because it is the most deceitful of the databases that we found. When you replicate from a writer to a reader, you would think that setting synchronous replication will guarantee that anything you have written and committed to the writer, an immediate read on the reader, you will see that change that was made. And the answer is no, it won't. It could take upwards of 1 second before you actually see the data change, despite having used what they call synchronous replication. And the reason for that is that synchronous replication does not guarantee the data is available on the remote node. It just means that the change data has been replicated to the remote node. It has not yet necessarily been applied to the remote node. So the data won't be lost if your writer goes down, but you can't necessarily read it immediately either. Now, the idea of replication lag detection is having logic that makes a decision on where to read data from that is replication lag aware. It knows how long it takes for changes to go from server A to server B. And it knows what tables were written to when. And you may be thinking, wait, that sounds familiar. Doesn't cache need to know what tables were written to when? The answer is yes. And ReadWrite Split is actually, when you think about it, another form of caching. Okay, except that you're caching the entire data set on another database node. Now, you're not caching the result sets, you're caching the raw data. So to do a read-write split decision, you're actually making a cache decision. Is that cache over there, i.e. on the reader, appropriate at a given moment? Now, if you're dealing with a table that is not written too often, you can almost always use the reader. If you're doing a ledger table that is written to every second, you probably can't necessarily rely on that to be accurate on the reader. Okay, effective read-write split keeps track of all this information and makes intelligent decisions at the moment it's needed to figure out where to pull the data from. Okay, it is very common for an application to do an immediate read of a table it just wrote to. And naive implementations of read-write split will often break the application because they're not aware of replication lag, last write times, etc. Transaction logic just makes things even worse. Okay. And then as you add more database nodes, the problem just becomes worse and worse as well. Okay. Now, what Heimdall does in order to understand how everything works and to do so in a vendor neutral manner is that we actually write a table that keeps track of a timestamp. So every say 100 milliseconds, we write to this table, and then we can immediately read from the reader what the timestamp is that's visible in that table as the most recent timestamp. Through that, we can adjust when the writes happen, and we can, as far for the replication lag detection, how frequent they happen. And we can estimate the safe time window in order to do reads against a database. So this is adaptive, and it will work with basically any replication type in order to figure out when is it safe. And then we only write or read from a reader when it's safe to do so based on the table by table. Okay. Now, there's no way to really do this unless you've already implemented cache logic. And that's the tricky part that most people don't understand. They think read-write split would be an easy part where caching would be harder. But the fact is, read-write split builds on caching. Okay, still looking for some questions in the chat. Okay, now let's talk about transparent database proxies, because a proxy can make a lot of these tasks easier for you if they implement the functionality on your behalf. So database proxies, Heimdall, obviously, we've got automated failover. That's another feature that we can talk about. These other proxies do as well. ReadWrite Split, these other products claim to support it, but they don't do the replication lag detection. So they do a very naive, you create a rule, it tries to use the reader. Proxy SQL does some very primitive replication lag detection, but it doesn't actually, it's about if the lag is too much, it just turns off a reader. Okay. Heimdall is database vendor neutral, supporting SQL Server, MySQL, Postgres. It does the automated cache invalidation and implements all the techniques I've mentioned for reducing latency. Okay. When should you use an in-memory data grid versus a database proxy like Heimdall? Well, if you're doing greenfield development, sometimes you can get better results than using a generic solution. But that difference may be a matter of you get 100% of possible cache hit capability versus 90% for something like Heimdall. And in that case, is it worth that extra 10% of benefit in order to versus the amount of development effort it'll take? If possible, if the proxy solution is good enough, then you know what? Go for it. Okay, and here's how we implement our solution. You've got either Heimdall operating as a driver, a JDBC driver, or as a proxy layer. And there's all these other functions. I haven't even gone into everything because we are focusing on just the scalability part, the caching and read-write split. But you have other things like connection multiplexing and pooling that are available as well. Okay, and this just kind of covers how we're packaged. We can either run as a proxy as an agent, or we can operate as a JDBC driver. Okay, and that would allow supporting of things like Oracle. Okay, now this is just a very simple deployment diagram. The way that it would work with replication lag detection is that the proxy would be doing the write of the timestamps against the writer and then read from the readers, and will from there be able to pull the estimated replication lag. There are additional controls so that you can adjust how sensitive the proxy is to replication lag. And then you can also add additional overrides to say, well, detect the lag, but then add, say, 5 seconds to the estimated lag in order to account for potential spikes to ensure security when you're doing the replication lag detection for read-write split. Okay, and just kind of summarizing the entire Heimdall database platform, you've got your application, you've got all these features from the caching, read-write split, failover. We can even do batched inserts, which in some particular environments like Redshift can dramatically perform or improve performance and preventing the need to rewrite applications to leverage Redshift better. Okay, we also have connection pooling and active directory authentication. The interesting thing about that is that we can actually synchronize the authentication tokens into the database as part of going through the proxy in order to ensure that your users that are active on the database correspond with what's in the Active Directory. Okay. We also provide, just as an example, a dashboard that gives you real-time metrics to show you what's going on, queries per second, what your cache hit rate is, and everything that we do is rule-driven. So you can be very selective about what content you're caching. You can drill down to a table level. You can drill down to individual queries. You can even drill down to turn on caching for one particular user, but not another if you wanted to. Well, if there are not going to be any questions, I will jump in, and I'll jump in on the dashboard here. Okay, so this is our dashboard. I'm actually showing live data. We've got the traffic going through for a particular application, traffic generator, and you can see that we do have caching enabled, and we're getting a 90% cache hit rate. I'm going to come in here, I'm going to change this, and you can see how easy it is. This is the cache rule that we have implemented, and it's basically saying cache everything. I'm going to disable the cache rule, and you can see what happens for the performance. So we went down from about 1,800 queries per second through the application down to about 1,200. And you can see the performance difference. Before, with caching enabled, we had about 300 microseconds average response time. When we disabled caching, it went to about 2 milliseconds. So about 6-7 times slower. And that's actually quite representative of what we see when working with customers. This 90% cache hit rate, you may think, oh, that's way too high. That's actually not uncommon that we get performance like that. Usually it's above 70%. Okay. Additionally, we can come in, I'm gonna pause that again. I'm gonna come over here and we can uncheck the reader eligible. And if we go back here as well, we can see again the impact. Now I'm kind of reversing by turning things off instead of turning things on. You can see before we had most of the traffic coming from the reader, the secondary node. Now that we've turned off the reader eligible rule, it's pulling the traffic from the primary node instead. So it's now coming from the writer. And this is just demonstrative of how this works. It's actually very easy to leverage the read-write split capability and the caching capability because of all the built-in intelligence that's been put into Heimdall. Okay. Again, if there are any more questions, please let me know. And otherwise, I think I'm done for the moment.
Awesome. I don't see any questions. All right, if there are no other questions, then Erik, maybe we can wrap up. Did you have any closing comments?
I don't think so. Actually,
right.
You know what? Let me pull up the very last slide. Okay. If you have any other questions, feel free to visit our website, www.heimdalldata.com. We're also available on the AWS Azure and soon the GCP Marketplace, and we're partners with all these fine companies. Okay.
Awesome. Thanks, Erik.